Greeting our judges, my name is Berang and my teammate here is Rikwa, and today we are going to present you guys about our remote supervising and auto-tracking solar panels. So first of all, the reason behind our project is that we noticed solar power is a promising and renewable energy source, and on the market, the efficiency of any panels that we found were around 20%, and we believe that we could bring about changes in this point. Now moving on to our main objectives, we aim to create a double navigation frame that could track and rotate the system, a self-charging model that could supply the system, and a mobile app with an online Firebase to upload information. Now in terms of construction methods, the whole system consists of mechanical components, hardware and software, and the procedure is divided into 4 main steps, as you can see down below. As for operating principles, the operating principles includes 3 main principles: the charging principle, the auto-tracking principle, and data collecting. About the charging principle, the panel will charge the battery after going through 6 capacitors, which will flatten the unstable electric current. The battery will then be used as a power source to operate the control board, the servos, and the sensors. A switch is also attached to change the power source between the battery and the panel when needed in maintenance. In terms of auto tracking, we use 2 servos and create a 2-axis turntable. The servos are attached to 2 reduction gears to raise the momentum generated. The sensor have 4 photon resistors at 4 corners with barriers between them for accuracy increase. The processor will compare the 4 resistors value and identify the sun's incident angle. And then it will ensure that the servos rotate until the 4 values are closely equal. And to provide remote supervising to user, we use the model ESP8266, which can connect to the Wi-Fi. The values of the panel and the battery are sent to the model and uploaded to a mobile application through a database, which in our case is the Firebase provided by Google. And now, Quang will continue with the result of the project.
So after several tests, we got some promising results. If you look at the graph, you can see that the power is the highest when the panel is perpendicular to the sun rays. The panels can produce the total of 45 watt electric current. However, 5 watt are lost because of the errors while spinning, and another 5 are used to operate the control board. Therefore, only 35 watt are used to charge the batteries. Moving on to the app, our app functions perfectly with an 1-second delay. This delay is to separate the flows of data and make the app got them more precisely. And moving down below, you can see that in this graph, the total power produced by our auto tracking system is much larger than the other two, the fixed 90 degrees system and the fixed 45 degrees system. The total energy produced by our system is around 406 watt-hours. However, for the 90 degrees fixed system, this is only 254 watt-hours, which is approximately 1.6 times lower than our system. In conclusion, we believe that we have successfully built the new system with acceptable errors and delays. The energy produced by the new system is around 1.6 times higher than the original one. And to improve our project, we believe that we can apply this in large industrialized system. By labeling the panels, we can determine the broken panels and therefore reduce the labor force and time in maintenance. This is the end of our presentation, and thank you for listening. If you want to see how our system operates, you can scan the QR code in the next slide. Thank you.